Okay, everyone, so we're going to get started on Mechatronics 2. So just pause on the pot stuff for now because we have another exercise before that. Anyway. So today we'll be going through a couple of basics, right? So the first thing is debugging. We're then going to go into state diagrams, other common software patterns that you might need to get used to, and then communications, electrical components, and then just some extra peripheral exercises. And so let me take out some stuff here and hand it around. Actually, if I want to come around, it might be a little bit easier to tell you. If you can bring that as well.
Okay, is it a voltmeter or multimeter? No, it has irons in it.
All right. Does anyone have a live circuit? Like a circuit that's working?
I don't know.
Does anyone know? Okay.
Yes, you guys do.
You guys have to do?
Yeah, do you have a live circuit?
You have a real circuit that's working? Circuit, yeah. Okay, yeah. Can we take a look at it?
Yes.
So, is there a power plug?
One, I can just take away the. Here's the button. Here's the button. Oh, no, it doesn't.
Yeah.
Yeah, all right. Right, they're on live. Oh, okay. Right. So actually, before we jump into this, I'm just going to show you live here as well. But what you can do, so confusion. So when you're sort of EE debugging, right? Two of the things that it's going to open. Two of the things that most often come up is just make sure your connections are correct. So that's why you always have a circuit diagram to start off with. Vision trying to open up. Make sure you have a circuit diagram. You make sure your connections are correct. Okay, that's one of the most most common errors that you're ever going to get. And then make sure the polarity of your components is correct as well. So I was, I think, telling some of you that we were doing a project for 2 weeks and we spent 3 days trying to debug a circuit, and just one of the components was backwards, right? And that took us 3 days to figure that out, right? Because we didn't go back to basics and sort of just spent time trying to think of those other issues. Okay, now. Other stuff as well is to make sort of really nice electrical circuit diagrams. So Fusion, I was actually just playing around with Fusion. And what you just do is you go to new design, new electronics design. And then you just create new schematic here. And then it allows you to place like different components. So for example, you can even get the Arduino Uno here. Oh, Arduino, this one here. So this is the Uno R3 shield that you have, right? And then you just like drag this onto here and then you just place it there like that. So pretty cool. And then you, for example, might want a resistor. So again, you just sort of scan through and find what a resistor. So say we want like the US style resistor. So you put this on here, you drag. And if you want to rotate it, then you can do that, for example. And then say you want like a ground. So this is a very sort of classic on ground. So just find a ground that works. This works, or okay, this one works. Touch it there, and then when you're done, you just click net here, and then you draw like a connection, like that. Okay, so that's how you sort of like make a nice circuit diagram, and then you can just export it however you like. So that is a function you need to be aware of. All right, so the first tool we're going to use, so if we can actually connect up this circuit, so can you bring your laptop and connect it up properly when you have the multimeter? All right, cool. So this tool here is called a digital multimeter, right? And it's a simple tool that measures voltage, resistance, and current. Okay, so this is to measure and figure out the signal you might be getting, for example, in your circuit, right? Although this is even more basic than that. You can have a couple of functions. So this is a display. This is a much older one. this is the dial, but they sort of all operate the same, and these are the banana plugs, and they're called banana plugs because I tried to look this up, but apparently this looks like a banana. Let me get it out. Does this look like a banana? I don't know, right? Someone thought that looked like a banana at one point, so they're like, all right, it's a banana plug. Maybe it's the part inside here. There, you can see inside there. It looks like a
Still a bit of a stretch.
Still a bit of a stretch. Anyway, it's called banana plugs. That name is stuck. Now, how the different sort of components are built is there's going to be usually four components, and sometimes it's in different orders, but you have one to measure resistance, one to measure current, one to measure DC voltage, and one to measure AC voltage. And how you tell the difference is the tilde is the AC voltage, and then DC is always a straight line because it's always a sort of single voltage. And so here we have the direct voltage one, the AC one, the current, and then the resistance down here. Okay. All right. Now there are sort of three banana plug things down at the bottom here. Generally, you want to use these two here. So common MAV resistance. So basically, this here just stands for common, which is ground. So you always have to have the black one in com. Okay. And then MAV, this is such a weird thing, but it just basically means that you can measure milliamps, voltage, and ohms. Okay. So that's all it stands for. That's usually the red one. So as you've probably learned now, we always use red for live and then black for ground, right? And then you only use 10 amps when the current is above 200 milliamps. Okay, so it's just sort of a special feature. All right, now you can have all types of banana plugs. So you have test probes, which is what we have here. So these ones here are called test probes, really sharp, right? You sort of just put it in there like that. You also have alligator clips. So alligator clips are these style ones here. So they look like an alligator clip, right? And then you also have an IC hook, which we don't have, but it's basically a hook that you can sort of retract out and then sort of hook onto sort of like a part of the circuit. All right, now measuring the voltage, right? So what you do is you place these probes. So firstly you turn the device on, and then we want to turn it on to DC in this case. And for example, we can set it to 20 volts, right? And then, or maybe, yeah, 20 volts should be fine. And then you basically just stick it like this between two different components, okay? So let's take a look at the circuit here. So what circuit do you have in it? So you have a stepper
This
motor,
is
right?
button one.
Yeah.
And then here's a stepper motor one.
Okay.
So it's like kind of like two different.
Yeah, and what is this resistor attached to?
This one is to the ground, so this part is the ground.
Okay, and this is the button? Is that
Yeah,
right?
yeah.
Okay.
This is the button.
And the resistor is attached to the button, is that right?
Yeah.
Okay. Let's say there's a voltage in this. So what do we expect this value to be? Well, the button's not pressed, right? Oh, so therefore it should be 0. I'm expecting, right? So hence it's 0. If you press the button. Up, yeah. So it goes up to -4.3. So do you remember our TTL logic? If it's above 2.2, then it considers it a 5, right? Yeah. In this case, it's 4.3, so I can change the polarity of this, and then I'm going to expect to see positive 4.3. 4.3. So what it really operates at is 4.4. Okay, does that make sense? So that's how voltage works, and recall that voltage is sort of a difference in potential just across the component, right? So that's how you measure voltage. Okay, and then the next, if it's too high, it simply reads a one dot. Okay. Yeah.
The number that you set it to on the multimeter itself, like the 20 stuff.
Yeah, so it's just different ranges, right? So for example, if I want to measure up to 1,000 volts, right?
Yeah.
Then this is going to give me like 200 or whatever, right? Because we're not operating at that level, we're operating at 5 volts, and so I've set it as 20 because the next one I believe is 2,000 millivolts, which means 2 volts, so it's going to be too low to read. So for example, if I try this is not going to break the multimeter or anything, but if you try this, it's probably going to say 10 is my guess. Yeah, see? So 1 dot means it's too high for that way. Yeah. Okay? Yeah. And it's the same here, so this is for 200. So again, it's just more precision with the lower ones. Yeah. But it can't measure high ones. Right? Yeah. Okay. So measuring resistance. Now what you can do as well is measure resistance. So if someone can hand me a resistor, so any resistor. Give me one. So what resistor is this? Sorry, yeah, 330, okay. So 330 is set to say, for example, 2000 there, and then you basically just run it like this. Does that make sense? Yeah, so again, resistors have 5% tolerance, we have to find a particular one, right? But again, if it's overloaded, then we'll say 1 dot. All right, and now measuring current. So how that works instead is you actually need to insert, and we're not going to do it because I don't have the alligator clips, but you need to insert the multimeter into the circuit, right? So it needs to complete the circuit. Does that make sense? Yeah. So for example, there we have a simple LED circuit with a resistor. You see how the multimeter has inserted itself into the circuit. That's how you detect it. Okay. All right. So next one now. So what if you've accidentally overloaded the multimeter? So all multimeters have a fuse in the back, right? Where you actually, so a fuse is an electrical component that is designed to break in the case that a circuit overloads. Like it is the component that will definitely break. And so how it works is you simply just replace it, and that just costs $50 a J car. All right, cool. So that's multimeter. So feel free to play around with that if you want to debug the circuit. The second is the oscilloscope. Now this here is a much sort of bigger thing to have, right? And so what it does is it measures an electrical signal over time, okay? So these are the different things that it can measure, right? And are particularly good at. So frequency, duty cycle. So for example, we have a duty cycle or PWM, right? Rise and fall times, which is a more sort of advanced feature, amplitude, mean, max, min voltages. Take a look at noise, look at phase differences. So some peripherals require you to be able to control phase, and then also the shape and waveform. So for example, is it a sine wave? Is it a sort of DC thing, right? And so this is how a multimeter actually works. And so we have on the x-axis is time. Okay, so this is time, obviously. This here is the voltage. Okay. And then what you need to check is your units. And so we have the units here, which is each block here is 500 nanoseconds. Okay. And then each block here is at the bottom here, which is 10 volts. Okay, and I'm capable of I can pretty much change that using these dials here. So for example, if I go down far enough, then you're just going to see noise, right? Yeah. Noise. So I've now changed it to 200 millivolts per square there. And if I want to change time as well, I can go down to microseconds or go up. Down to nanoseconds, go up to microseconds, and go to milliseconds. Okay, and then now as well, another important thing to check is what's the active channel. So as you can see here, I've got the yellow of this first channel here, which corresponds to this switch here. So you can also have a second channel as well for something like this. Okay. So one thing that, or things that I often use it for is to check for the voltage, the waveform, the duty cycle, and the frequency. So for example, for something like this, what would be the voltage? Sorry? Well, no, what's the voltage on this graph?
Oh,
Yeah,
this graph, sorry.
One.
Sorry?
Is it the one?
Yeah, so it goes from, in this case, I believe it's like negative or positive 2.5-ish, right? To negative 2.5, right? And that could also indicate that it's a one that's being sort of pulled down, right? From 0 to 5, for example. What's the duty cycle of this? Yeah. No, duty cycle is a percentage, recall. So it's the time in which it's on. So it's 50%. Yeah. Okay. Waveform, this is called a square wave for obvious reasons, right? It's sort of like a sine wave, but square. And then what's the frequency of this?
1.5.
Say that again, sorry.
1 over the period, right?
Yeah, so 1 over, it's going to be 1 microsecond, right? So it's 1,000 1000 hertz, okay, like 1 kilohertz, excellent. Okay, so now that's the screen, right? And then what we have on the right here are the dials that you need to use, okay? So these vertical dials here deal with the vertical component, right? Which means that you're controlling the voltage. Okay, so for example, I can increase or decrease the voltage steps there. You can take a look there. See how it's like steps of 2 volts now, and then it can be steps of 15 millivolts. Okay, and then this one here deals with time. So I previously had like 1 second, right? And then now I have 10 milliseconds or 5 milliseconds. Okay, and I can go to microseconds as well. Okay, and now these top dials here are for the decision. So for example, if I want to center this on 0, then I just use this dial here to center it on 0 like that. Okay, time you don't center it as much because it's usually just in the middle like that. And then these ones here are to do with the resolution, which one look at the oscilloscope. And now other stuff as well. If, for example, I have 2 channels and I want to turn one of them off. So for example, if I want to turn this off, or I want to go into the menu, then I can click that, right? So that goes and brings me into the menu. It can also turn off the signal as well. And these here are the things that I connect, and these are called B and C connectors. So if you take a look at this, how B and C connectors work is it has this sort of groove here. You put it in like that, and then you make sure you turn it and click into place. Okay. All right. Now I don't have the IC hook, but I have the alligator clips for this one, right? And so how this works is you can have a ground, which is always black, and then a red, which is live, right? And so how that works, for example, if you want to watch a signal. So is there a signal? What's the signal for the stepper motor?
Signal,
Yeah.
the button.
Sorry?
You mean like what trigger is it?
Yeah. Are you sending a PWM signal to the stepper motor, or what do you do?
No, I just directly set it. Like, use the button. So when the button is pressed, it will.
Yeah. Okay. So where's the?
Start the setting.
Let's see if I can figure out the live. Do you know which is the PWM signal from the stepper?
It's just at 9:11 because it's like fixed. We don't really need to set any.
Sure.
It's not
That's fine.
right.
Okay. So let's just figure it out for this resistor here, right? Okay. So if I want to figure out this resistor here, I'm going to change this. I know that it's going to spike to 5 volts. So I'm going to change the resolution up to 2 volts per box, right? And so we're going to expect to see a line, for example, right? I can also do 1 volt. If it's 1 volt, then I expect to see a line here. Okay. And then another thing is time. Time is probably less important for this one because it's just going to appear or not appear. Okay, it does something. Disappears though. Signal. There we go. Okay, so we have it on negative, and you see how it's just spiking down like that. Okay, pretty cool. And then if I want to see it sort of longer term, right, I can increase the time. So it's like every 5 seconds or every 2 seconds. So obviously with this, it's a lower sampling, so you see sort of lower resolution. Yeah, so you can see how I can see it over time now when I'm drilling, right? See that? So it captures that trace. Okay. Awesome. So that is how you use an oscilloscope. Now, other things you might see as well on more advanced probes is this attenuator. The default is 10x, and you only want to use 1x if it's for very low voltages or very low frequency. Okay, so just default to 10x. All right, that's it. So that's our demonstration. So now I'll go into state diagrams. So yeah, thanks so much for the. Yep. Okay, so state diagrams. So state diagrams are a very powerful tool when it comes to mechatronics, right? And it is something that's well worth learning. So it represents a set of states and transitions between states, right? And allows you to model pretty much anything. So we're going to practice creating some state diagrams ourselves. Now, this is sort of into computational theory. So for those who are interested in computer science, right, it's actually called finite automata in computer science. So you might end up seeing that around if you go deep enough in computer science. And more powerful in computational theory, actually 2 different types of things called context-free languages and Turing machines. But these aren't as applicable for events, right? So you don't often see them in mechatronics. Now, what is a state diagram? So there are a couple of rules when you're creating state diagrams. The first is that states are represented as circles. Okay. So if you're in a certain state, you want to create a circle and then label that state. Okay. So for example, you could be in the waiting state. The second rule is that you usually have more than one stage. Okay. So depending on your sort of creation, right? Like for example, if we have a garage door or something, it might be in a door open and a door closed state. Okay. So it might have completely different states. The third is that the arrow here that we have with the dot at the end indicates the starting state. Okay, so when you look at a state machine or state diagram, you automatically know where you should start in the state diagram. Okay, and that's represented by this arrow here with a dot. Does that make sense? And then arrows that don't have a dot but are between two states represent transitions. Okay, and these transitions all need to state two things. And the first is usually mandatory, but the second is optional, right? Which is a trigger followed by the actions. Okay, so what triggers it, followed by what actions you need to take. And that's represented or split by this / here. Okay, so for example, door closed, I press the door open button, and then it opens the door. Okay, and now I'm in the door open state. And then I press, for example, I close the door on something, or I press close door, whatever, and then it closes the door, and then you move here. Does that make sense? So in this case, I haven't pressed the closed door. I'm just thinking of a microwave. If I just simply close the door, then it now enters this door closed state. Okay. And it is possible to have a self loop, and this is just sort of the final rule. It is possible, for example, for you to be in the door open state. If you press start on the microwave, it's just going to loop back to the door open state because it doesn't really start the microwave. Does that make sense? Okay. So now I want you to try and create a state diagram that has the following functionalities. Okay, so work in your teams to draw one out. So you can draw one out either on a piece of paper or in your tables or whatever, with the following functionalities for a microwave. And I've gotten it started for you on the right there.
Okay. We do this on too. Sorry? Well, we can also do them with people.
Just drawing it out. It's runs
File. File and then you can electronic time. Alright. You want to draw?
Well, you know what? I think I knew what.
Huh? I can draw.
No. Okay.
You still get two arrows.
Yeah.
So, find the ball. So it's also gonna be two states, isn't it? You can start with the door closing door.
This isn't usually
Yeah, maybe, yeah.
It's G code. G code is the one after, where like you've done all the things.
Okay, so open the door when door open is pressed. Okay, so the door open is pressed, open. Oh, yeah, so it's the exact same thing. And then it looks like. Oh, you might have it, so, yes, but let's just do start only when start is pressed and the door is closed. So start is, so there's a line between door open.
Door closed.
Yeah, door closed. Just be a line between door closed and cooking. That, oh, yeah, good idea, yeah, close door frame for lamp, yeah, so narrow, just like, yeah. And then press start, start cooking. And also
It didn't really depend on whether it's
it's
like is it going back to
Press start.
start or you just continue cooking?
Press start,
Yeah, okay.
and then pressing.
Yeah, you just make it like that.
Yeah. And then pressing stop while closing the microwave, which will put it back to door closed, right? Okay, I usually go with it. Yeah, it'll be back. We'll go back to door.
What is this? Oh, true, but it's not that long.
Microwave, if you, I never press stop. I let it stop or I open it.
I never pressed
No, what if something,
open and it's
what if something exploded inside? What if something exploded inside?
Then I'd like,
You'd open the door, right?
Yeah.
Oh, I don't like open the door
No,
automatically.
but in this case, you can only open the door when the microwave is not cooking. Right?
yeah,
So it's like an
it's-
old-fashioned microwave. It's
have to
not all these old
okay, so, yeah, so. Cool.
Yeah, you
Press
press
stop.
stop, and then press open, you open.
Press stop, stop.
Yeah.
Yeah.
Yeah, this is all close A.
Is technically inside. No. Yeah, press stop.
Yeah.
Yeah, because you kind of.
Oh, I think like you want to write door closed here, DC, and NC for not cooking, basically. Yeah, we know. I got you. Press start after stopping. Wait, press, I'll stop. I'm not open the door. Open is, open is a loop. Oh yeah, fourth one is pressing start. I think it's like, as soon as you press start, it starts cooking, but you need to restart. So like, like, I don't think it's the same.
Over the button.
Goes back here. It's a closed state, not. And you press start, it starts with. No, you press it close, press stop, press and stop.
After stopping, I guess then you press the
You press. Then you manually stop it, like it's like 3 minutes. Yeah.
Yeah, so actually.
And actually, you can just use the same.
Does it save?
So start.
It's like, it's a big start.
So I feel like that. Stop looking exactly. You need to tell them.
Cooking, start cooking, but it uses the same values and it stopped at. Or like.
Stop the microwave. Stop it.
You stop it. You press that button. Down, yeah, it starts at 30 seconds.
Now, if say for example, we check.
Press start. And you just restart. Start again. So it started again. So it's right.
I think everyone's actually got it, so I won't even go through it. Everyone's got the right answer.
Yeah.
Now, just an additional question is, like, obviously when you're using a microwave and it's cooking, you can just press open door and it will stop as well. How would you modify the state diagram to account for that? So it's cooking, and then you press open door and it will stop cooking and open the door as well. So it's a single transition somewhere else. Yeah, that's good.
Cooking door, yeah. Cooking the door.
The one is open the door.
Door is low.
Door is low.
Cooking.
You already press open door.
Yep, that's right. And then what will the trigger action be? Press, yep, press open.
Yeah.
Yeah, stops cooking and opens door.
Yeah.
I mean, I changed the state to door open.
So we do like lines that they compose.
No, it's better to talk about it. Yeah. Press.
Roast everything.
Yeah.
You know,
This one, really, press start.
Oh, that's how it says.
You
just
stop it.
Oh, you can find this thing. Five.
Okay, so let's go through what this actually looks like in code, right? So I think everyone's finished. Oh, then car key time. Okay. Now before that, actually, so let's try and do a car key because then I have the code example in the car key. So try and write a state diagram for a car key, right? And I haven't started this off for you, but just think about how a car key works, right? Hopefully everyone understands what all those buttons do. So see if you can build a state diagram that meets this, and then we'll run through a piece of code that actually does this.
I know what coding is that one. Good man. Alright, okay, so lock state, unlock state.
Just remember, this is from the perspective of the car, right? Not the car key itself, right? The car key doesn't exist.
We should have both.
Only one unlock, right?
Yeah.
I think you probably had the instruction there, doesn't it? Okay, assume the car is on the start.
It's also the first one is black hole and red hole, yeah.
You, unlocks, right?
Yeah.
Alright, okay, pressing lock locks the car if it is unlocked.
One black hole, one red hole, yeah, just FYI, so I saw two holes in, I just wrote hole.
Oh,
For the last one?
Oh, yeah. Okay, so pressing unlock.
What did it just be a separate thing? Like the benzene, Oh, right.
Alright, we're here. Unlock. And then also pressing lock.
I mean, you see a problem.
Alright, pressing hold unlocks the boots regardless of whether the car is locked or not. So it doesn't matter.
It's like two.
So just think about how many states you probably have.
Yeah, it does, like, you always want to go back. Pressing A.
Maybe state in the car, like, no, yeah.
Yeah.
Yeah, so as the initial state is.
Oh.
Right.
But they're not infinite, so we have a press lock.
Yeah, so think about combining states, right? There are multiple potential combinations.
Turned on the alarm.
Because think about what a car looks like when you're looking at it, and it's locked, right? Food is not open.
Pressing hold.
Yeah, hopefully not. Yeah, serious issues.
Yeah, so another alarm state, or do you want to put a call? Alarm?
At the same time, the car is still locked.
Wait, so hold does both of these things?
No,
So can't we just put them together?
Are we gonna say that?
There's red hole and black hole, just FYI, yeah? Yeah, it's not the same holes, yeah.
Okay.
We're gonna say that when the so red is alarm.
Red is alarm, but okay, so I'll put
We're
B
gonna
here.
say that.
And then just press alarm. No, it doesn't. It doesn't. No, pressing unlock turns off the alarm. Okay, and then going from the alarm state to the unlock state. Pressing unlock turns off the alarm. Press.
You only do one transition.
A plus.
Was the door locked and unlocked it both?
My handwriting is actually not bad. Hi, good luck, guys. Oh yeah. You did. These two are the exact same now. That was
Oh, no, you are. Okay, sorry.
Yes.
You
You shorthand.
and then these two slots.
How to get out of here.
Again.
It's a state that you can never get out of.
And then so it would be like this.
Wait, where is it?
Close boot. Yeah.
Close
so
boot.
in the box.
Yeah, so physically close, but, that's what either unlock or not.
There could be two transitions, yeah, that's right.
These two circles in like.
So as you're making states, make sure there's a way to get out of all the states, right? There should never be a terminal state for the car.
Holds the button.
Essentially, that boots unlocks one.
There's
no way to get out.
manually. Because there's two holes. You just say close boot.
Boots, so button.
Unlock means up, right? Unlock means there's a pop out.
Just stop. Open, you know, even though I'm locked.
Yeah, well, the key like it, unlock it by you.
Yeah.
It's still automotive thing.
Yeah. This is the car.
So this depends on what car.
or something.
Some of the cars you get unlocked, it doesn't open it.
Oh, no. It's sort of finite.
You can unlock it, you don't want to open it.
You know, the video on.
Yeah, don't worry.
Historically, they've thought of one thing, and historically, my classics have thought of
We just follow what it says. Pressing hold, depends on the alarm. The pressing the alarm.
That's what we love.
Depends on the alarm.
Two different
Pressing the alarm,
things,
and
different
lock the
things.
alarm.
That doesn't happen anywhere else.
Okay, do you want to take a look at a solution? I believe this table here. Solution.
It's virus.
Oh,
Car is locked. So black hole.
perhaps it's not. Perhaps it would be pretty. Right, crowd.
Yeah, yeah. Let's take this close.
No,
Your solution.
So, because it has to be closed and locked.
Yeah.
Oh, so we can just have.
Close or adapted to it. How to get out of here.
And then we just go back to here.
via unlock.
Yeah.
By pressing unlock, yes, correct.
We haven't written any actual.
Yeah. Yeah, I can see that.
You can put it as boost
And,
unlock.
just
Door lock.
Yeah, you can put it as
So door lock.
then it's like you're going to unlock it is unlock.
Okay, press unlocked, great. Press lock,
But it's one of those totally different.
You have a slightly yeah. Maybe doors actually.
Yeah, I mean, I think the point when you
Yeah.
The thing about it, like, why would you have to and just have
I'm just remembering that he had police access.
do you want like to open order or something? Do we need it?
So what's the state? No, not right now. Like, is the car open?
Good question.
Well, it shouldn't matter, right? Because like if you're opening the boot, right, that's like the point of it, having like say you have automated tailgate, you just press it and regardless of whether or not you pass.
Yeah, but
Does the,
the car will be
I
nice.
don't know if the state of the lock.
Yeah, does it matter? Right, like, as in, it depends if you want to find a grain or state machine.
Yeah, I don't know if it's like.
So these guys here had a more fine grained version of the lock unlocked is open and open as well, right? So it could be interesting to take a look at because they took a slightly different approach to this. Any right, any wrong? I don't know. This doesn't-
Depends on like what cars you use.
What make cars is right there?
Mosh.
My father said that you could.
We'll take a look at their solution as well. So they enumerated more things.
Actually, it should go away with origin.
Because of that, we had the same state.
Yeah, but he had pretty fine, he said he had to get it.
Also, you need to do like.
Wow. Unlock, that's door closed.
Because then you can
Oh,
do
wait,
the
but-
same thing with the alarm. Would be like
Wow.
alarm on walls. Yeah, which was the discussion we had.
Yeah,
So trying to
yeah,
get
yeah,
yeah.
8 states, right?
Yeah.
You should out.
Yeah, not unlock, so that's specified. Unlock, good open.
Okay, cool.
More inefficient.
I went to the dock.
More elegant.
Yeah, that's more elegant, that's more like more, maybe more precise.
And with that combination of.
Okay, so let's take a look at what something like this looks like in code, right? So just a sort of dummy example, because that's gonna be really long. Let's say, for example, we have door closed and door open states, and then there are these different actions and triggers, right? And so what this actually looks like in code is that you need to specify a state. So the state could be, for example, door open or door closed. And if the state equals door closed, for example, then it detects a certain event. Does that make sense? So for example, it's like if the door is closed, then we check if the door open button has been pressed. Okay? And then if it has, then we open the door and then we change our state. Does that make sense? And then if, for example, the state is door open on that side, and if the door latch is closed, then we change our state to door is closed. And if the start button is pressed, then we do nothing. Does that make sense? So this is what it actually looks like in real code, and this is what's called the events. Or yeah, and so the next step, and like what this actually looks like when you're dealing with Arduino is, for example, could be digital reads and digital writes. Okay, so that's how you deal with state machines. And this is what's called the events and services framework, which is you're basically in different states. You detect for events, and then you do what's called a service. Does that make sense? So you'll see this terminology around mechatronics, but this is what that refers to. So it's just putting in code a state machine. All right, common software patterns. So we've talked about all sorts of common software patterns on Tuesday. Now, one of the sort of big ones that you might see commonly is when you're detecting, for example, a rising edge or a falling edge, which is what we did on Tuesday, right? And so really important, again, to just always have this sort of code structure where you're checking, for example, if the state has changed and the state is what you expect it to be. Okay? So again, just the structure that we saw on Tuesday, but a very common pattern that you see everywhere in mechatronics. Now, a related pattern that you might see, particularly for biological signals, is what's called a continuous event checker, which is when you have a sort of a continuous variable that can change over time. Okay, so for example, heart rate, sort of breathing rate, anything that's a real continuous number, right? So we've been dealing previously with discrete, which is it either is open or closed or 0 or 1. Okay, But obviously biological signals don't really work like that. It's always like, for example, from 0 to 100 or 0 to 1,000, right? And so what you need to do is something called hysteresis, right? So let's take a look at this signal here. This signal, for example, could just simply be someone's heart rate. It is this variable, okay? So when you're detecting heart rate, it is this variable. And so a big question is, at what point do you have a threshold, right? So for example, it's like if it's below 80 heart rate, then you do something, and if it's above 80 heart rate, then you do something else, right? Now, if we try and follow that pattern, as you can see, for example, if say someone's heart rate is higher than 80, right, then you activate your machine, right? If that's the case, you're going to activate it here, and then you're going to turn it off. And then you activate it here, and then you can turn it off, right? And then you can activate it here, turn it off. Then you're going to properly activate it here, right? So you see how it can be quite messy, right? If you have a single threshold. So the trick is actually to have two thresholds, called a lower threshold and an upper threshold. Okay, and this is a pattern in engineering called hysteresis, which basically just says that at this point here, you don't do anything. At this point here is when you turn it on. So when it passes the upper threshold, and then once you have that upper threshold, this threshold kicks into the lower threshold, and only when it drops below this lower threshold do you turn it off. Does that make sense? And the same applies. Once you pass here, then this upper threshold kicks into place, and it doesn't, the behavior of the machine or whatever doesn't change until it passes back past this dotted line. Okay? So what does it look like without hysteresis? It looks like this. You sort of turn it on for a little bit, and then you turn it off, right? And then with hysteresis, you have a very nice, smooth function. Okay? So what does that look like in code? So in code, it's again very simple. So say we have here, we're reading a light value, analog read rate. If the light value is below this threshold, then we turn on the light and then we switch the thresholds. Okay? And then otherwise, if it's above this threshold, then we turn off the light and then we switch the threshold again. So again, a very sort of simple software pattern, but it's something that really smooths the behavior of devices that you might have. Okay. Now, I previously talked about how delay is considered bad practice, right? So the question is why? So services you write. So we talked about the events and services framework. Any service that you write should be rapid and not block anything else from running. Okay. So this is okay again for this class, but it is not okay in the real world, and we'll talk about why. So what, like a common pattern that you will see in medical devices is that you urgently need to do something. Okay. So if, for example, you write blocking code and you're waiting 1,000 milliseconds or 1 second, right? You are blocking other code from running. Okay, and so for example, you might have a timer that runs every second, right? If you decide to put delay somewhere in your code, it's going to throw off that 1 second thing that you're doing. Does that make sense? It's not going to really look like 1 second, but it's going to look, for example, at some point like 2 seconds or 3 seconds because there's this delay. Does that make sense? So the delay sort of pushes everything back. Okay, so a common pattern that you'll see later on if you go further into mechatronics is something called interrupts, which is you urgently need to do something in the code at all costs, okay? And this is a very common pattern again for medical devices because, for example, if you detect an electrical shock, you need to immediately shut down the system within microseconds or milliseconds or even microseconds, okay? And I think the rules for medical devices is you need to shut it down within microseconds, okay? And so interrupts are a very powerful way to guarantee safety, okay? So again, Arduino has a whole interrupt library, but it does allow you, for example, to detect an electrical shock and then shut down the whole system extremely rapidly, thereby potentially saving the patient from electrical shock, okay? All right, now a quick note about communication. So these boards are very powerful for communications, and we'll just talk briefly about how these work. Again, there's like a whole world of understanding it, but there are sort of 4 or 5 main ways to communicate, right? So 4 or 5 main communication protocols that you'll see around. The first is UART. So UART is simple, it's over long distances. So there's always usually a trade-off between the complexity of the communication protocol and how far you can actually travel it. So the simpler ones can usually travel a lot further, right? But it has limited bandwidth. And UART only supports 2 devices. I2C is really good for multiple devices and short distances. And then SPI is good for high speed, simultaneous transfer and receive. So it's very, very fast, right? That's what's called full duplex. And it's very good for short distances. And then you also see Wi-Fi and Bluetooth. And these are generally just peripherals that you can buy and attach onto your Arduino. Okay, so again, very useful to have around. Now, how does each work? So sort of a very quick crash course on how each works. But both devices agree on a certain speed. A transmits individual bytes to B with a predefined start and stop bit. Okay. I2C is what's called a master-slave system. So a master specifies an address, sends data, and then waits for an acknowledgement from the slave, and then that's how it communicates. Okay. And then SPI is also known as a master-slave system with separate lines for each system. It selects a slave and then sends a signal. Okay. So again, just completely different protocols for how it works with different trade-offs. All right. Now, the next is a quick tour of the different electrical components that you will see sort of out in the wild. So recall that we always, when dealing with new electrical components, consider the components, the pins, the circuit, and the pseudocode that you're working with, okay? And this is going to be particularly true later for sort of the open-ended project. So some stuff that you might see. So you have in your pack actually digit displays, right? Which is just ways to represent digits, okay? So you can sort of have any numbers or potentially even letters on this digital display. Now you might also see liquid crystal displays. So in your packs are also a liquid crystal display. So you can actually display stuff on an LCD. And how they work is you basically have multiple layers of liquid crystals, and then it pushes out a light, okay? Now, sort of more advanced, and we don't have it in this pack, but you can actually buy for Arduino. It's what's called an OLED display, and that uses a different technology, which is a little bit more reliable than liquid crystal displays. You then have switches. So we've already played with switches, but there's all sorts of switches that you can use. Okay, so some people, for example, really like slide switches. So for example, in acoustics, people love slide switches, right? You can also have things like joysticks, which you can play with as well. But how switches are described is the number of poles and throws. So you might see, for example, 2P, 1T, right? What on earth does that mean? So poles is the number of circuits that you can connect. So for example, this is one circuit, right? And then throws is the number of possible output connections. So this is 1P and 1T, right? This is, you can only have one connection, so it's 1P, but it is 2T because there are two possible output connections. Does that make sense? Okay, so you always see that when you're designing electrical circuits. All right, this is a shift register. So you also have this in your pack as well. And we're not going to play around with it, but it does allow you to increase the number of pins, okay, that are connected to the Arduino in particular. So it allows you to extend the number of pins you have by, I think, by another 8 or 16. Now, you'll also see things called drivers in your pack. So the drivers have been used for stepper motors, for example, or certain LED matrices. But many components require more power, which is the purpose of a driver. So it increases the current, increases the power and voltage that you can actually use. Now, we're going to be playing around later with what's called a potentiometer or a pot, right? This particular one is called a trim pot, but it's basically allowing you to tune voltage with a diode. So it turns the voltage into an analog value. Accelerometer, so I think we have a different type of accelerometer, but you will see this one where it actually detects acceleration in 3-axis and then reports the values back to you. Hall effect, so you'll see this again in your packs. It's called a Hall effect sensor. This is a magnetic field sensor. Okay, so it allows you to actually put a magnet there and it's going to return a value indicating the magnetic field strength. Okay, sometimes it's also called a Hall effect switch, which is it turns on only when there's a magnet there. Temperature sensors you can play around with. This is what's called a thermistor. So this is a resistor that changes resistance with changes in temperature. Okay, so if you think about things that require certain temperature requirements, like ovens or microwaves or whatever, there's often a thermistor inside the device. Photoresistors. This changes resistance when light is shined on. Okay, so we'll actually get to play around with it later. Photodiodes, this produces a current in response to light, so just a different way of manipulating light to electricity. Transistors, now this allows you to control a larger current with a smaller current, okay? So this has been sort of the key things on chips. Everyone's been sort of making smaller and smaller transistors, and this has led to sort of like really cool devices that we can now use. Infrared communication, so there is an infrared emitter, infrared receiver, which is usually black, and then the remote control, which is also infrared. So every sort of TV remote you use, PS2 controllers, they all use infrared. Okay, so they all use infrared to communicate with the TV or the PlayStation or Xbox. Operational amplifier. So you'll see this in your kits as well, but this is a tunable voltage amplifier. So it amplifies the voltage. Okay. What if you really want high voltages? So for example, if you're dealing with very high frequency, high voltages, these small components aren't good enough, okay? So you need to use things like real signal generators, which you now sort of know how to program using mechatronics, and also, like, for example, a radio frequency power amplifier. Now, this is a tool that I didn't realize existed, but I learned about when I was doing startups, which is an isolation transformer. This isolates the power of your device from the electrical grid, and it actually guarantees electrical safety. So it's a very, very powerful tool if you ever decide to go into medical devices. All right, optocouplers. This is another really cool technique I learned about while studying implants. And this is a technique where you can isolate one electrical circuit, which is, for example, really high voltage, from another much smaller one on the implant side, right? And that way you can guarantee that your device actually doesn't have any electrical shock risk to the patient while in vitro, right? And so how that works is it uses an infrared LED in one circuit, and then it communicates information to a phototransistor on the other side. And therefore, this gap here guarantees that there's a huge sort of voltage difference, right? You can operate at really high voltages in this circuit and then really low voltages in this one, and it's still going to work. All right, servo motors. So last two. The first is servo motors, so you can get to play one. These are easy to use motors with very high torque. It allows you to have a fixed rotation angle with PWM, right? And it's not great for continuous movement. So it breaks if you try and sort of continuously move it. And then the final one is steppers. So this is ideal motors for example, wheels. So anything we need sort of constant movement, right? More powers, more pins, a little bit more complex motor. And so servos are usually a lot cheaper, a lot easier to use, but steppers are required when you need sort of continuous movement. Okay, and there's a whole world of peripherals out there. So I just took some pictures of some here, but I found, for example, like an MP3 player, a rain sensor. You can use like an ECG heart kit, so you can actually build your own ECG. You can build your own heartbeat sensor, right? So something similar to what the Apple Watch uses, and you can even do like an air quality sensor as well. So there's all sorts of peripherals that you can use with Arduino. Right, always read the data sheets and manuals, right? So just get used to it, like particularly later for one of the projects, and make sure that it operates at 5 volts. Okay, so Arduino always operates at 5 volts or 3.3 optionally, right? So just make sure that whatever you're using actually operates at that level. Okay. Now, peripheral exercises. So this is first exercise. Actually, let's go to lunch and then let's come back because I realize how late it is now. So let's come back at 1:45, and then we're going to do some exercises, and then you can sort of close off and prepare your slides, that sort of thing. Okay, so I'll just leave these exercises for you guys to do if you want to try after today or you want to do at home, right? But these are just useful exercises to practice it as well, whoever's just taking the kit. So try like an LED which tunes based on the dial adjusted voltage. Okay, so that's just learning how to do analog read and analog write. And then, so we skip through this. Oh yeah, so this is how a potentiometer works. So it's a variable resistor that changes resistance based on dial. So at its lowest point, it still does have some resistance, and this is the symbol here. And the lines here are pretty critical. So it's like red is 5 volts, black is 0 volts, and then this middle one is the one you're actually trying to analog read. Okay. This is how a potentiometer actually works. So there's ground here, VCC here, 5 volts here, this is the output. And you have a resistive strip whereby it increases in resistance quite literally as you wipe it, right? As you shift it. Pretty cool. Let's moving forward. So you can always refer back to this later. This is a potentially useful function to be aware of. Some of you have already seen this, where it's like if you're mapping from one range, so for example, 0 to 1023 to 0 to 255, this is just a really useful function that just immediately maps it for you. Right. Another good practice is this LED, which turns on when it gets dark and off with light. And so the component you need to use is a photoresistor or light dependent resistor. You have one in your pack, it's pretty cool, you can play around with it. Essentially what you do need to do is what's called a voltage divider circuit. So you basically have, for example, the photoresistor here, and then another resistor here, because the photoresistor doesn't have sort of an internal resistance when it's light or dark, right? And so you then read out this voltage here. And if you take a look at the specs of the photoresistor, go back here. So when it's 10 lux, which is roughly the light of a street lamp, right? So that sort of light, then the resistance of this component here is 5 to 10K. And then when it's dark, it's 200K, okay, or 0.2 million ohms. Okay, so in order to sort of solve this, the order that is better is to have the photoresistor down here and then the resistor up here. The reason being because the voltage for this is not inverted, so it's a little bit easier for you to understand. And which resistor would you choose? You need to make sure that that would be at least, for example, 10K. If you choose 330, then this is always going to be very high regardless of what that resistor there is, if that makes sense, regardless of whether it's light or dark. Okay? All right, so move along. You need to use hysteresis if you'd like a sort of smooth thing. Other things as well is just use a pod to control a servo motor. Some of you already worked with servo motors now, which is cool. These are some useful functions you can have in Arduino. Moving forward, pod to control a stepper motor. So again, same sort of principles. In order to work with a stepper motor, you need to have a stepper motor driver. Okay, so it's just one of those components where you need sort of extra current or extra voltage requirements, extra sort of stability in the current voltage, and so you have to use what's called a stepper motor driver. And Arduino also has a stepper library that makes it really easy to use. So I think CJ here has been using that, which is really cool. And then yeah, just when you come home, like create a system with one input, or if you're already done with your 3D printing stuff, create one input and output of your team's choice. And so there's some really cool stuff there. For example, you can make a joystick do something, or you could have like a remote, infrared remote control to turn on the stepper motor. Just like cool stuff. Okay, and then we'll end here. So just the rest of the time is just preparing for tomorrow, any slides and website as well. Cool. Put them there.